Hey everyone, welcome! Today, we're going to tackle a really fundamental concept in programming performance, space complexity. It's all about figuring out how much memory your code really needs to get the job done.
You know, whenever we're looking at an algorithm, we're really asking two main questions. First, how fast is it? That's time complexity. And second, how much memory does it hog? And that, my friends, is our topic for today, space complexity. Think of them as the two sides of the same performance coin.
Okay, here's the game plan. We'll start by comparing time and space, then we'll nail down a solid definition for space complexity, learn the lingo of Big O, see it all in action with some actual code, and then wrap up with why this is so critical.
All right, so let's get right into it. When we talk about the space an algorithm uses, what are we really measuring? It's actually a bit more nuanced than you might first think. And this is a super important distinction. We are not talking about the memory the input data itself takes up. We're focused on the extra memory, the scratch pad, if you will, that the algorithm needs to do its work. It's the memory overhead of the process.
Now, this might look a little intimidating, but I promise the idea behind this formula is actually super simple. It's just made up of two key parts, a fixed part and a variable part.
So that C you see, that's your constant space. Think of it as the fixed cost, the memory for your basic variables and the code itself. This part never changes. And then you've got SP. This is the part that changes, the memory that grows or shrinks, depending on how much data you're feeding the algorithm.
And figuring this out isn't some kind of dark art. There's a pretty clear four-step process we can follow. You just have to spot all the variables, figure out which ones scale with the input, add it all up, and then describe it using some special notation.
Okay, so to really talk about this stuff like a pro, we need to learn the lingo. And in the world of complexity, that language is called asymptotic notation. It's just a standardized way to talk about how things grow.
This table right here is huge. It breaks down the three main ways we talk about this stuff. You'll hear developers throw these terms around, but the one we really care about most of the time is Big O. Why? Because it describes the worst-case scenario. It answers the question, what's the absolute most memory this thing could possibly use? And for building reliable software, that's the question you want answered.
Let's start with the absolute best-case scenario. This is O1, or constant space. This is like the holy grail of space efficiency. It means no matter how much data you throw at it, 10 items or 10 million, the extra memory it needs to do its job stays exactly the same. It doesn't grow at all.